Seasons in America are starting to feel wrong. Winter arrives late, then hits hard. Spring shows up early, then suddenly freezes. Summer lasts longer, burns hotter, and autumn no longer cools the way it used to. Across the country, weather patterns that once felt familiar are becoming harder to recognize. This is not just strange, it is a warning sign. In tonight's video, the evidence reveals why America's seasons are no longer acting normal, what is driving the shift, and why scientists are paying close attention. Before we begin, please like the video, subscribe to the channel, and turn on notifications so more people can discover stories like this. High above the land, the broad patterns of air begin to shift in ways that are slow, steady, and measurable. The atmosphere over North America no longer behaves with the same regularity that once defined the passing of seasons. Layers of air, extending from the surface up through the troposphere, hold heat differently than in earlier decades. The troposphere, the lowest layer where weather forms, gradually warms as energy accumulates within it. This added energy does not distribute evenly, and the imbalance alters the movement of air across vast distances. The jet stream, a fast-moving river of air that circles the northern hemisphere, plays a central role in guiding seasons. It flows from west to east, driven by differences in temperature between cold polar air and warmer air to the south. In earlier conditions, this temperature contrast remains strong, and the jet stream maintains a relatively stable path. Now, observations indicate that the Arctic region warms more quickly than lower latitudes. This process, known as Arctic amplification, reduces the temperature contrast that powers the jet stream. As a result, the jet stream weakens and begins to meander. These meanders form large northward and southward bends. When the jet stream curves north, warm air extends farther into regions that once remained cool during certain times of year. When it dips south, cold air moves into places that would normally be warming. These movements do not follow the steady progression of seasons that once guided expectations. Instead, they linger, sometimes holding a region in unusual warmth or persistent cold for extended periods. The atmosphere responds to increased greenhouse gases, which trap outgoing heat and keep more energy within the system. Carbon dioxide, methane, and other gases absorb infrared radiation emitted from the surface. This trapped energy raises average temperatures, but it also increases the amount of moisture the air can hold. Warmer air holds more water vapor, and water vapor itself acts as a greenhouse gas, reinforcing the warming effect. This feedback loop contributes to a more energetic atmosphere. With more energy available, the structure of seasonal transitions begins to change. Spring does not always arrive as a gradual warming. Instead, sudden shifts occur when warm air masses move quickly into colder regions. Autumn does not always bring a steady cooling, as warm periods may persist long after expected. Winter air masses weaken in some years, allowing above-average temperatures to dominate large areas. In other cases, displaced cold air lingers far from its usual domain. Large-scale pressure systems, which guide weather over weeks and months, also show altered behavior. High-pressure systems can become more persistent, holding clear skies and stable conditions over a region. When these systems remain in place, they block the usual movement of storms. This blocking pattern leads to prolonged dry periods in some regions and extended wet conditions in others. Low-pressure systems, which bring clouds and precipitation, may follow unusual paths or stall in place. The polar vortex, a region of cold, circulating air high in the atmosphere near the Arctic, also interacts with these changes. When the vortex remains strong, it contains cold air near the pole. When it weakens or becomes disrupted, fragments of cold air move southward. These disruptions connect with the shifting jet stream, creating episodes of extreme cold in regions that are otherwise warming over long periods. Such events contribute to the sense that seasons are no longer consistent. Temperature averages over the United States show a gradual increase over many decades. However, the change is not uniform across all seasons. Winters warm more quickly in many areas, reducing the duration and intensity of cold periods. Summers extend in length, with more days reaching high temperatures. The transitional seasons, spring and autumn, compress or stretch in ways that vary by region. In some places, spring begins earlier, while in others, late cold spells interrupt early warmth. Atmospheric circulation also influences the distribution of precipitation. Warmer air increases evaporation from oceans, lakes, and soils. This moisture enters the atmosphere and later returns as rain or snow. When the atmosphere holds more moisture, precipitation events can become more intense. Instead of frequent moderate rainfall, some regions experience longer dry periods followed by heavy bursts of rain. These patterns disrupt the expected rhythm of seasonal moisture. Cloud formation responds to these changes as well. Clouds reflect sunlight and trap heat, depending on their type and altitude. Alterations in cloud cover affect how much solar energy reaches the surface and how much heat escapes back into space. These subtle shifts contribute to local variations in temperature and seasonal timing. Wind patterns at different heights in the atmosphere also change. Surface winds respond to pressure differences shaped by larger circulation patterns. When these patterns shift, the direction and strength of winds change accordingly. Winds transport heat and moisture, linking distant regions. A change in wind behavior can bring unexpected warmth, dryness, or humidity to an area, further altering seasonal experience. The timing of seasonal milestones becomes less predictable under these conditions. The first frost, the onset of sustained warmth, and the arrival of consistent rainfall all depend on atmospheric stability. When the atmosphere becomes more variable, these milestones shift from their historical averages. Observations indicate that these shifts differ across the country, reflecting the complex interplay of regional and global influences. Despite these changes, uncertainty remains in how specific patterns will evolve year by year. Climate models, which simulate the behavior of the atmosphere based on physical laws, indicate general trends of warming and increased variability. However, the exact timing and location of specific events remain difficult to predict with precision. The atmosphere is a complex system, sensitive to small variations that can influence larger outcomes. Across the broad sky over America, the structure of seasons continues to transform. The changes begin in the highest patterns of air, where energy flows and pressure differences shape the conditions below. These shifts do not occur abruptly, but emerge through gradual alteration of long-standing processes. The result is a new pattern that still resembles the familiar cycle of seasons, yet no longer follows the same steady path. Around the edges of the continent, the surrounding waters hold and release heat with a slower rhythm than the land. This difference gives the oceans a steady influence over seasonal timing in the United States. Water warms more slowly than soil and rock, and it cools more slowly as well. Because of this, the Atlantic Ocean, the Pacific Ocean, and the Gulf of Mexico act as large stores of thermal energy, shaping the air that moves inland. As these waters warm over time, the seasons they help govern begin to drift from their older patterns. Sea surface temperature is a simple term for the temperature of the uppermost layer of ocean water. This layer matters because it exchanges heat and moisture directly with the atmosphere. When sea surface temperatures rise, the air above the water also tends to become warmer and more humid. Winds then carry that air toward the land. In this way, the oceans do not remain at the margins of the American climate. They reach inward through moving air, changing storms, clouds, rainfall, and the dates at which warmth or coolness settle over the country. The Atlantic Ocean influences the East Coast through a broad boundary between ocean and land that runs from Florida to New England. In winter, the ocean can soften cold outbreaks near the shore, especially when coastal waters remain warmer than the air passing above them. In summer, the ocean can reduce daytime heating near the coast while raising nighttime temperatures, because warm water continues to release stored heat after sunset. As the Atlantic warms, this balancing effect changes character. It does not simply make every season gentler. Instead, it alters when cold arrives, how long summer-like warmth lingers, and how much moisture remains available for storms. Along the southeast and mid-Atlantic coasts, warmer ocean waters can support more humid air for longer parts of the year. Humidity is the amount of water vapor in the air. Warm air holds more water vapor, and when ocean temperatures rise, evaporation increases. That added moisture does not remain only over the sea. It moves inland with onshore winds and with storm systems forming near the coast or crossing from ocean to land. This helps create warm seasons that feel longer, heavier, and less clearly separated from the transitional months that once marked spring and autumn. Farther north, the Atlantic also affects the timing of winter along the northeast coast. Cold season conditions still occur, but the boundary between rain and snow becomes more sensitive to slight changes in temperature. A storm that once would have brought snow may now bring cold rain near the coast, with snow confined to higher ground or inland areas. This shift changes the character of winter without removing winter entirely. Observations indicate that the cold season in many northeastern coastal areas now contains more interruptions, more thawing periods, and less durable snow cover than in earlier decades. The Pacific Ocean governs the western edge of the country in a different way. Along the west coast, ocean temperatures and currents shape the marine layer, coastal fog, and the general moderation of seasonal extremes. The Pacific often keeps coastal California, Oregon, and Washington from reaching the severe winter cold or intense summer heat found farther inland. Yet this moderation now sits within a warmer background climate. Coastal waters have experienced periods of unusual warmth, including marine heat waves, which are extended stretches of above-average ocean temperature. These events affect air temperature near shore and may weaken some of the old signals that separate one season from another. The Pacific also feeds large weather patterns that move eastward toward North America. Storms form over the ocean and carry moisture toward the western United States, especially during the cooler half of the year. When sea surface temperatures and atmospheric patterns over the Pacific shift, the paths and intensity of these storms shift as well. Some winters bring repeated storms that drench coastal regions and mountain slopes. Others bring fewer storms, leaving long dry intervals where wet season moisture would normally accumulate. The result is not a simple new normal, but a more unstable seasonal pattern tied closely to the changing state of the ocean. The Gulf of Mexico exerts a powerful influence over the south and the central part of the country. Warm Gulf waters provide a major source of moisture for the lower atmosphere. This moisture moves northward into the Mississippi Valley, the southeast, and the plains. In spring and summer, it helps fuel thunderstorms, heavy rainfall, and humid heat. Because Gulf waters are warm for much of the year, they help blur the edge between seasons in the southern United States. As the Gulf warms further, warm and humid conditions can persist longer into autumn and appear earlier in spring. This does not mean the seasonal calendar disappears, it means its boundaries grow less firm. The air arriving from the Gulf can create summer-like conditions on dates once associated with milder spring weather. It can also sustain warmth later into the year, delaying the more settled coolness that historically followed autumn fronts. In some years, strong cold air still pushes southward and briefly restores the older feel of winter, yet those intervals often occur against a warmer and moister baseline. Ocean influence also extends through large recurring climate patterns. One of the most important is El Niño Southern Oscillation, a natural cycle involving changing ocean temperatures and atmospheric conditions in the tropical Pacific. During El Niño and La Niña phases, storm tracks and rainfall patterns across the United States can change noticeably. El Niño often shifts the southern branch of the jet stream, bringing wetter cool seasons to parts of the southern United States and milder winter conditions to some northern regions. La Niña can support different patterns, sometimes favoring drier conditions in the southwest and wetter conditions in the Pacific Northwest. These natural patterns have always affected American seasons, but they now act within an atmosphere and ocean system that is warmer than before. This added warmth can strengthen some effects and complicate others. A familiar ocean pattern may still recur, yet the temperatures, moisture levels, and storm outcomes linked to it no longer match historical expectations exactly. Researchers continue to study how natural variability and long-term warming interact. Observations indicate that both matter. The oceans still pulse through their recurring patterns, but the background state in which they do so has changed. The contrast between land and sea remains one of the basic engines of seasonal timing. Land responds quickly to sunlight, heating and cooling in a matter of days. Water responds slowly, storing and releasing heat over longer intervals. That slow response once helped stabilize the edges of the American climate. Now, because the stored heat in the oceans is increasing, the stabilizing influence itself is changing. The sea still delays and moderates, but it does so from a warmer starting point. At the outer edge of the continent, the altered rhythm of the oceans quietly reshapes the air that reaches the land. The result appears in delayed cool seasons, earlier humid warmth, uncertain snow lines, and storms carrying more moisture than older seasonal memory would suggest. These changes begin not on the roads, in the forests, or over the farms, but offshore, where the surrounding waters hold the heat of a changing world and pass it inward through every season. Along the outer rim of the country, where land meets ocean, the seasonal year takes on a quieter but increasingly unstable form. Coastal regions do not usually experience the most extreme highs and lows found deeper inland. Water tempers the air, sea breezes move coolness ashore by day, and stored ocean heat returns to the atmosphere by night and through the colder months. This long-standing balance still shapes the American coastline, yet the balance now rests on warmer seas, rising air temperatures, and shifting rainfall. The seasons remain visible, but their boundaries soften, stretch, and at times lose their old sequence. From the Gulf Coast to the Atlantic seaboard, winter arrives with less force in many locations than it once did. Freezing air still appears, and severe cold still visits at times, but the average cold season now contains more interruptions. A sharp cold spell passes, then a broad return of mild air follows. Trees and grasses receive mixed signals. Soil that once remained cold for longer periods now warms during breaks in winter weather, along much of the southeast coast. This pattern produces a season that still bears the name of winter, while often carrying the feel of late autumn or early spring. Near the shore, this moderation is not new in itself. Coastal climates have always been buffered by nearby water. What changes is the baseline from which that buffering begins. When the adjacent ocean is warmer, the softened winter becomes softer still. Overnight temperatures remain higher. Frost occurs less often in some places. The number of days with a lasting chill declines. This does not erase cold weather, but it changes its persistence. A colder pattern may arrive, yet it often fails to hold the coast for long. Spring along the coast also begins to lose some of its older steadiness. Instead of a gradual passage from cool to mild, some regions experience abrupt pulses of warmth, followed by cooler marine air, then another surge of heat. The coast sits at the meeting point of these competing influences. Inland air masses move outward. Ocean-shaped air moves inward. As large atmospheric patterns shift, these exchanges become less predictable in timing. Seasonal transition starts to feel uneven, not because weather has become random, but because the forces guiding it now operate within a warmer and more moisture-rich system. Humidity becomes one of the clearest signs of this altered rhythm. Humidity refers to the amount of water vapor in the air, and coastal air naturally holds more moisture because of constant evaporation from the sea. When the sea and the air both grow warmer, that moisture load increases. Spring warmth, once light and dry in some coastal areas, now often arrives carrying heavier air. Summer then builds from a higher starting point. By the time the hottest part of the year settles in, coastal nights remain warmer and the atmosphere retains more moisture after sunset. These warmer nights are an important part of the seasonal shift. Human attention often settles on daytime heat, yet nighttime cooling helps define the shape of a season. When nights stay warm, the body, the soil, the buildings, and the roads release less heat before the next day begins. Along the coasts, especially in the south and parts of the northeast, this means that summer no longer depends only on afternoon extremes. It persists through the full daily cycle. The absence of cool nights lengthens the felt season of heat. Rainfall also changes character along the coast. Warmer air and warmer ocean water increase the amount of moisture available to storms. In many places, the result is not simply more rain spread evenly through the season. Instead, rain may arrive in stronger bursts. A coastal front stalls, a thunderstorm train forms, a tropical system moves slowly. Hours of intense rain fall where seasonal memory expects an ordinary wet spell. Then a stretch of relative dryness follows. The total pattern becomes less regular. Seasons used to be known partly by the reliable pace of wet and dry intervals. That pace now weakens. On the Gulf Coast, this shift is especially visible. Warm water lies close to shore through much of the year, feeding moist air inland. The old line between late spring and full summer becomes less distinct as high humidity arrives early and lingers late. Autumn, too, changes character. Cooler air may begin to move southward, but the nearby Gulf continues to release heat and moisture. This delays the establishment of stable cool season conditions. The calendar moves forward, while the atmosphere seems reluctant to follow. Farther up the Atlantic coast, the signs are different but related. In the mid-Atlantic and northeast, cool seasons still retain stronger contrast than in the far south, yet snowfall near the coast grows more fragile. Slight differences in temperature now matter more than before. A storm tracks northward with abundant moisture, but surface temperatures hover just above freezing. Rain falls where snow once accumulated. Wet snow changes to cold rain. Snow cover, if it forms, often disappears quickly during the next mild interval. Winter scenery becomes more temporary and the season loses some of its continuity. Sea level rise adds another quiet layer to this change, though it does not alter air temperature directly. Higher sea levels allow coastal flooding to occur more often during storms, high tides, and strong onshore winds. Flooding that once belonged mostly to exceptional events can now accompany ordinary seasonal weather under the right conditions. This changes how the season is experienced on the ground. A storm no longer needs to be historically severe to produce disruptive coastal water levels. Seasonal storms become more damaging because the physical boundary between sea and land has changed. Along the Pacific coast, the pattern differs again. The cool eastern Pacific and the coastal upwelling of deeper water have long helped maintain milder summers and narrower seasonal ranges, especially in California. Marine air, low clouds, and coastal fog often define the warm season. Yet this system also shows strain. Marine heat waves reduce the contrast between cool water and warm land. In some periods, fog patterns shift. Coastal waters remain unusually warm, and the old cooling influence weakens. Summer then grows hotter near the shore, or arrives with less of its former restraint. In the Pacific Northwest, coastal storms still mark the cool season, but the intensity and timing of rainfall can shift. Warm ocean conditions, combined with atmospheric rivers, can bring large amounts of moisture ashore over short periods. An atmospheric river is a narrow corridor of concentrated water vapor moving through the sky. These events are natural, yet in a warmer atmosphere they can carry more moisture. Along the coast, this means wet season rain can become more intense, while dry season conditions may still persist for long stretches. Salt marshes, tidal flats, beaches, harbours, and barrier islands register these changes in quiet ways. Plants respond to altered flooding frequency. Sand moves under stronger storm waves. Estuaries receive pulses of fresh water and salt water in different patterns than before. These are not separate from the seasons. They are part of how the coast expresses the season, through water level, vegetation, wind, cloud, and the timing of storms. When the seasonal rhythm changes, the coast changes with it. Across America's coasts, the old moderation of the sea remains present, but it no longer produces the same familiar sequence. Winters grow less settled, springs less gradual, summers longer and heavier, and autumns slower to cool. The coast still lives by the ocean's rhythm, yet the rhythm now carries more heat, more moisture, and more interruption than the generations before had come to expect. Across the breadth of the United States, the movement of storms creates one of the clearest structures in the seasonal year. Storm tracks are the usual paths followed by low-pressure systems, fronts, and bands of strong wind as they travel through the atmosphere. These paths help determine where cold air settles, where rain falls, where snow accumulates, and how quickly one season gives way to another. When storm tracks shift, even slightly, the familiar order of the year begins to change. The land still passes through spring, summer, autumn, and winter, but the transitions become less reliable, and the weather within each season grows less even. A low-pressure system forms where air rises and pressure at the surface decreases. As air rises, clouds develop and precipitation may follow. Around these systems, warm and cold fronts mark the boundaries between contrasting air masses. A front is a zone where warm air and cold air meet. Along these boundaries, the atmosphere becomes active. Winds increase, clouds gather, rain, snow, or thunderstorms may develop. In the United States, the repeated passage of these systems once gave many regions a recognizable seasonal rhythm. Autumn brought a growing sequence of fronts and cooler air. Winter delivered frequent low-pressure systems along expected routes. Spring brought unstable air and changing fronts. Summer storms developed in more local and heat-driven ways. This pattern remains in broad outline, but it no longer behaves with the same consistency. The paths followed by storms depend on the jet stream, on ocean temperatures, on the contrast between warm and cold regions, and on the pressure patterns that rise and weaken across continents and oceans. As these larger conditions change, storm tracks bend, slow, drift northward, or at times become blocked. A storm that once would have crossed one region may now pass farther north. A front that once moved through quickly may now stall. A rainy period that once belonged to a week may now compress into a single intense event. In the cool half of the year, storm tracks over North America often guide Pacific systems into the west, then carry new low-pressure systems across the plains, the Great Lakes, and the Northeast. These tracks help set the boundary between cold northern air and milder southern air. When the track lies farther south, colder air spreads more widely and snow becomes more likely across the central and eastern states. When the track lies farther north, warmth reaches deeper into the country and precipitation falls more often as rain. Observations indicate that in many areas the average position of some winter storm tracks has shifted, contributing to milder winters in certain regions and changing the distribution of snow and rain. This shift does not happen in the same way every year. Natural variability remains strong. Some winters still produce repeated southern storm tracks and widespread snow or ice. Yet over time, many regions experience a reduced number of cold season days that remain steadily below freezing. This means storms increasingly arrive in air that sits close to the threshold between snow and rain. A slight warming, even of only a few degrees, changes the result. Snow turns to sleet, sleet turns to rain, and the season takes on a different character even when the storm itself remains strong. Spring reveals the instability of shifting storm tracks in another way. During this season, the United States often lies between lingering cold air to the north and rapidly warming air to the south. This contrast helps fuel strong fronts and storm systems. In a warmer atmosphere, spring can begin earlier in some places, but cold air still remains available farther north or aloft. The result is an uneven season marked by sharp reversals. A warm spell settles across a region, plants begin to grow, and then a late-season front pushes through with frost or freezing temperatures. Storm tracks help deliver these reversals, and when their timing becomes less predictable, spring loses its old steady progression. Across the central United States, spring storm tracks also influence severe weather. The meeting of Gulf moisture, dry western air, and cooler northern air creates zones of strong instability. Instability is the tendency of air to keep rising once it begins to rise. Rising warm, moist air can build powerful thunderstorms, especially when winds change with height. Shifting storm tracks alter where and when these ingredients overlap. Some years see severe storms concentrated farther east or earlier in the season than expected. The broad pattern remains familiar, but the geography and timing no longer fit historical averages as neatly. Summer has its own storm structure, though it is less dominated by broad cold fronts than the cooler seasons are. In many parts of the country, the jet stream retreats northward in summer, and local heating becomes more important. Yet storm tracks still matter, because they determine where storm clusters travel, where humid air pools, and where stalled boundaries remain in place. In a warmer atmosphere, the air can hold more water vapor, so when summer storm systems do form, they may produce heavier rainfall. A slow-moving summer low or a stalled front can deliver repeated downpours to the same area. Instead of the season feeling like a long warm period broken by ordinary thunderstorms, it may become a sequence of hot, stagnant intervals interrupted by very intense rain. Autumn once served in many regions as a calmer transition, with gradually strengthening fronts, cooler nights, and a steady retreat of summer heat. Now autumn often becomes uneven. Storm tracks may remain displaced northward, while warmth lingers over broad areas. Then a stronger pattern abruptly arrives and drops temperatures quickly. In some years, tropical moisture from the Atlantic or Gulf interacts with autumn fronts, producing heavy rain far inland. In others, blocking patterns delay storms and leave large areas dry well into the calendar season. The result is a less stable descent into winter. Mountain ranges also interact with storm tracks, redirecting moisture and shaping regional contrasts. As storms cross the west, mountain slopes force air upward, leading to cooling and precipitation. Small changes in storm path can greatly alter which basins receive rain, which slopes receive snow, and which valleys remain dry. When the track shifts, one side of a range may experience a wet season while nearby areas remain under clear skies. This creates strong regional variation and contributes to the sense that the seasonal map of the country is no longer fixed. Blocking patterns deepen these effects. A blocking pattern occurs when a large high-pressure system becomes nearly stationary and prevents the usual west-to-east movement of weather systems. Under a block, storms are diverted, delayed, or weakened. One region may endure prolonged rain while another sits under persistent dryness or warmth. Because these blocks can last for days or weeks, they stretch particular weather conditions beyond what people associate with the normal pace of a season. A rainy spring becomes a flooded spring. A dry autumn becomes a season of dust and wildfire risk. A warm winter becomes a long period of bare ground. Scientists continue to study how global warming influences the frequency, position, and persistence of storm tracks and blocks. The atmosphere remains complex, and confidence is stronger for some trends than for others. Observations clearly show that warmer air increases moisture, that snow-to-rain boundaries shift with rising temperatures, and that many regions are experiencing changes in the timing and character of storm-driven seasons. It remains uncertain how every regional track will evolve in detail, but the broad signs of change are already visible in rainfall intensity, winter precipitation type, stalled systems, and uneven transitions. Storm tracks once acted like moving lines in a seasonal script, carrying the country through repeated phases of cooling, warming, wetting, and drying. They still perform that work, but their routes and tempo are changing as they wander, stall, or migrate. The American year becomes harder to recognize by its old sequence. The land still waits for fronts, for rain bands, for snow-bearing lows, and for clearing skies behind them. Yet the order in which these arrive, the form they take, and the time they remain now drift farther from the older pattern that once made each season feel settled in its place. Across the southern belt of the United States, the warm part of the year no longer holds its older boundaries. Heat arrives earlier, remains later, and settles more deeply into the daily and nightly rhythm of life. From eastern Texas across the Gulf states and into parts of the southeast, the seasonal pattern still includes winter, spring, summer, and autumn, yet the balance between them shifts toward prolonged warmth. This region has always known long summers and humid air, but observations show that the duration and intensity of heat are increasing, especially through warmer nights, more frequent heat waves, and shorter intervals of lasting coolness. The south lies close to major sources of warmth and moisture. The Gulf of Mexico supplies humid air through much of the year. The low latitude of the region allows strong sunlight over long portions of the annual cycle. Broad high-pressure systems in the warmer months often suppress cloud formation and allow heat to build near the ground. These basic conditions are not new. What changes is the background climate in which they occur. Average temperatures rise. Soil loses moisture more quickly under heat. The atmosphere holds more water vapor. Together, these changes reshape the seasonal character of the region. Spring in the south often begins with rapid warming. This has long been part of the regional climate, yet the warming now starts from a higher base. Mild winter days become more common, and episodes of warmth arrive earlier in the calendar year. Trees may leaf out sooner. Grasses begin active growth earlier. Insects emerge in larger numbers during warm spells. Yet the early start does not always mean stability. Cold fronts still move through, though often for shorter periods. As a result, spring can feel less like a gradual opening season and more like an early extension of summer, interrupted by brief returns of cooler air. Humidity strengthens this effect. Warm air that contains large amounts of water vapor slows the body's ability to cool through evaporation of sweat. The atmosphere, therefore, does not merely register higher temperatures. It changes the physical burden of heat in the southern states. This matters because humid air is present across much of the warm season and increasingly during its edges as well. Days that once felt like late spring can now carry the weight of midsummer air. Autumn days may continue to feel heavy and warm well after the calendar suggests a seasonal shift. Nighttime temperature is one of the most important markers of this change. During clear nights, the land releases heat back into the atmosphere and space. In a drier and cooler environment, that process can bring meaningful relief before the next day begins. In the south, high humidity and increasing greenhouse gas concentrations reduce this cooling. Clouds can also trap outgoing heat. Urban areas add their own stored warmth from pavement and buildings. Though the broader pattern extends far beyond cities, the result is a region where nights remain warmer than in the past and where heat accumulates across consecutive days. When nights fail to cool, the season itself changes shape. Summer becomes not only hotter but more continuous. It no longer depends on a limited set of peak afternoons. It occupies mornings, evenings, and sleep hours. Heat waves become more dangerous because there is less recovery between them. A heat wave is a period of unusually hot weather lasting several days or longer. In the south, these episodes often combine high air temperature with high humidity, making them more stressful for people, livestock, crops, and outdoor infrastructure. Observations indicate that many parts of the United States now experience more frequent and more intense heat waves than in earlier decades, and the South remains especially exposed because of its moist air. Rainfall patterns also help define the warm season. The southern states receive moisture from the Gulf, local evaporation, and storm systems moving in from the west or forming in place. Warmer air increases the amount of moisture that storms can contain. This means that rainfall may come in more concentrated bursts, especially during thunderstorms or tropical systems. Yet between those events, long, hot, dry stretches can still develop. The season then takes on a pattern of extremes, days or weeks of punishing heat, followed by intense rain, then a rapid return to warmth. This differs from older expectations of more regular intervals between rainfall and heat. In many southern areas, autumn no longer begins with a firm retreat of summer. The angle of sunlight still lowers as the year progresses, but the atmosphere remains warm for longer. Gulf moisture continues to move inland. High overnight temperatures persist. Cold fronts arrive, yet some lose strength before reaching the deepest south. or else they pass through quickly and are replaced by warm air again. The result is a delayed cool season. Leaves may change later in some areas. Grass may continue growing further into the year. Insects remain active longer. The cultural signals of autumn appear, but the air itself often lags behind. Winter, too, changes in the south, though not by disappearing. Cold weather still occurs. Freezing nights still arrive, especially inland and to the north of the Gulf Coast. Snow and ice still affect the region from time to time, sometimes in severe and disruptive ways. Yet the average winter has grown milder in many places. Cold spells may be shorter. The number of frost days declines. Warm intervals interrupt the season more often. This makes winter less continuous and less defining in the annual cycle. Instead of a stable cool period, some southern areas now experience a season of alternating mildness and brief cold incursions. This altered seasonal balance affects the land itself. Soils dry more rapidly during prolonged heat. Plants that depend on winter chill may receive fewer cold hours. Winter chill refers to the amount of time spent in cool temperatures that some plants need in order to flower or fruit normally. When these cold periods shorten, agricultural timing may change. Fruit trees, ornamental plants, and some native species respond differently depending on the amount and timing of winter cooling. At the same time, a longer warm season can expand growing time for some crops, while increasing water demand and heat stress for others. Fire risk also grows in some southern landscapes, especially where heat combines with drought and dry vegetation. The humid south is not uniformly fire-prone in the same way as some western regions, yet periods of unusual dryness can still create conditions for grass fires, woodland fires, and smoke episodes. This is another way in which the season becomes less predictable. A region associated with moisture and green growth may suddenly move through a period of crackling dryness under prolonged heat and wind. Wildlife responds to these changes through altered breeding, migration, feeding, and shelter patterns. Though those deeper ecological effects belong to later layers of the subject, at the outer level of the southern climate itself, the main change is simple and persistent. The warm season expands. It presses into spring. It lingers into autumn. It reshapes winter into a shorter and less settled interval. The south still follows the turning of the earth around the sun, still receives winter light and summer light in their expected order. Yet the lived climate between those celestial markers has shifted. Across the southern heat belt, the old seasonal calendar remains visible but faintly redrawn. The names of the seasons stay in place, but the weight of the year shifts toward heat, humidity, and prolonged warmth. What was once a region of long summers becomes a region where summer-like conditions claim more of the year, and where the cooler seasons retreat into shorter, more fragile spaces between expanding months of heat. In the southwest, the seasonal year is shaped by dryness before it is shaped by cold or heat. This region includes deserts, plateaus, dry basins, and scattered mountain systems across areas such as Arizona, New Mexico, Nevada, southern Utah, inland southern California, and parts of western Texas and Colorado. Here, the air often contains little moisture, the sky remains open for long periods, and the land responds quickly to sunlight. Under these conditions, the changes in season have always depended on a delicate balance between winter moisture, spring warming, summer heat, and the arrival of seasonal rains. That balance is now shifting. The dry lands still move through the same annual cycle, but the transitions grow less dependable, the heat grows more persistent, and the moisture that once defined certain parts of the year becomes harder to count on. Dryness gives the southwest a wide daily temperature range, with little water vapor in the air and often little cloud cover. The ground heats strongly under daytime sun and cools quickly after sunset. This creates a climate in which hot afternoons and cool nights can belong to the same day. Yet as average temperatures rise, even this familiar pattern changes. The nights, though often still cooler than in humid regions, do not always cool as much as they once did. Heat lingers longer in the ground and lower atmosphere. During prolonged hot periods, the difference between day and night narrows. The region retains its dry character, but the relief once offered by cooler nights becomes less reliable. Winter in the southwest has long played an outsized role in shaping the rest of the year. Much of the region depends on cool season storms for a significant share of annual moisture. These storms come from the Pacific, crossing the coast and moving inland with rain for lowlands and snow for higher ground. In some years they arrive frequently enough to moisten soils, feed streams, and build mountain snowpack. In other years they remain sparse. This natural variability has always defined the region. What changes now is the background of higher temperatures, which increases evaporation and causes a given amount of precipitation to go less far. Evaporation is the process by which liquid water changes into vapor and enters the air. In hot, dry environments, evaporation can remove water quickly from soil, plants, and open water surfaces. A warmer atmosphere also increases what scientists call evaporative demand, which is the atmosphere's tendency to draw moisture from the surface. Even when rainfall does not greatly decline, the land can become drier because the air demands more water from it. Observations indicate that this process is an important part of increasing aridity in the southwest. Aridity means the long-term condition of dryness in a region, shaped by the balance between incoming moisture and water lost back to the atmosphere. This helps explain why the seasons feel less stable in the southwest. A winter may bring some storms, but warm conditions can reduce snow accumulation and dry the surface quickly afterward. Spring then arrives with soils that already hold less moisture than they once did. Dry soil heats faster than moist soil because less energy is spent evaporating water. More of the sun's energy goes directly into raising temperature. This creates a feedback loop. Dryness supports heat, and heat deepens dryness. Spring can therefore shift rapidly into extreme warmth, with little of the mild interval that might once have separated cool season moisture from summer intensity. The old rhythm of spring in the southwest often includes windy, drying weather. As pressure patterns shift and the land warms, strong winds move across open terrain. These winds lift dust from bare surfaces, carry dry air across valleys and plateaus, and increase the loss of moisture from soil and vegetation. In a warmer climate, when winter moisture has been limited and snowpack has declined, this windy part of the year can become harsher. Dust storms become easier to form where land is exposed and dry. Fine soil particles rise into the air, reducing visibility and affecting health. The season is no longer only a passage between winter and summer. It becomes a period of environmental strain in its own right. Summer in the southwest has always brought intense heat, yet current conditions raise that heat beyond older expectations. Persistent high-pressure systems often settle over the region in the warm season. Under high pressure, air sinks. As it sinks, it compresses and warms, which discourages cloud formation. This allows more sunlight to reach the ground and further strengthens the heat. When such systems remain in place for days or weeks, extreme temperatures spread across large areas. Deserts, paved surfaces, rocky slopes, and dry vegetation all absorb and radiate heat. The season then becomes broader and more continuous, less a defined part of the year than a dominant condition lasting across multiple months. Heat also changes how the body of the land behaves. Streams shrink earlier, small ponds dry, surface moisture disappears quickly after rare rain. Plants close their pores to conserve water, slowing growth. Some lose leaves or enter a dormant state, which is a period of reduced activity used to survive stress. The landscape may appear still, but this stillness reflects pressure rather than balance. The summer season presses heavily on every exposed surface. One of the most distinctive features of the Southwest is the North American monsoon. A monsoon is a seasonal shift in wind and moisture that brings a marked change in rainfall. In the Southwest, this usually develops during the warm season when heated land and changing circulation patterns draw moist air inland from the Gulf of California, the eastern Pacific, and at times the Gulf of Mexico. Thunderstorms then build over mountains and deserts, often in the afternoon or evening. These rains can offer temporary cooling and local relief. They also carry risk, because dry soils and steep terrain do not always absorb intense rainfall well. Water runs off quickly, leading to flash floods. The monsoon remains a core part of the seasonal identity of the Southwest, but it has become more variable in timing, location, and strength. Some years bring delayed onset, patchy rainfall, or long breaks between storms. Some storms produce intense downpours over small areas while leaving nearby places completely dry. Warmer air can increase the moisture available to storms, but drought, altered circulation, and higher land temperatures complicate the pattern. Observations indicate that the monsoon has not vanished, yet its reliability has weakened in ways that matter deeply in a region where seasonal rain is precious. Autumn often arrives quietly in the Southwest. Day length shortens, and overnight cooling becomes stronger, but the land may remain very dry after summer heat. If the monsoon has been weak, autumn can begin with parched soils, dry grasses, and stressed forests. If the monsoon has been active, some areas may briefly green, only to dry again under warm days and clear skies. The season therefore depends strongly on what came before it, rather than serving as a stable reset. Autumn often reflects the accumulated gains or losses of the previous months. Winter returns with the possibility of renewal, but that renewal is less certain than before. Rainfall may come, or may miss the region. Mountain snow may build, or may fall as rain at lower elevations that once held snow longer. The cool season still matters because it offers the best chance for replenishing water in soils, rivers, and reservoirs. Yet in a warmer Southwest, the margin for error narrows. A modestly dry winter now carries greater consequences because evaporation, heat, and long warm seasons amplify every moisture deficit. Across these dry lands, the seasons still turn in their expected order, but they no longer bring the same balance of relief and stress. Winter moisture is less dependable, spring dries faster, summer heat expands, and seasonal rain arrives with greater uncertainty. The Southwest remains a land of open sky, sparse clouds, stone, sand, and distant mountains. Yet the climate that moves across this landscape grows more severe in its dryness and less steady in its timing, making the old calendar of the desert harder to trust from one year to the next. Above the dry basins and plateaus of the west, the mountains hold a different seasonal clock. Elevation changes temperature, wind, cloud formation, and the form in which water falls from the sky. As air rises over higher ground, it expands and cools. This cooling allows moisture to condense into cloud and, when temperatures are low enough, into snow. For much of the western United States, mountain ranges have long served as cold reservoirs, storing winter precipitation in frozen form and releasing it slowly as the year warms. In that sense, the mountains do not simply receive the seasons, they preserve them. Yet the preservation is weakening. The high country still marks winter more strongly than the deserts below, but its calendar no longer holds as firmly as it once did. The great ranges of the West, including the Sierra Nevada, the Cascades, the Rocky Mountains, and many smaller uplands, create layers of climate stacked by altitude. At lower elevations, winter may bring rain, brief cold, and occasional snow that melts quickly. Higher up, the same storm may deliver deep snowfall, long-lasting cold, and a snow cover that endures for months. This vertical arrangement once produced a fairly clear sequence through the year. Autumn cooled the ground. Winter built the snowpack. Spring began the melt. Summer exposed rock, meadow, and forest under a dry sky. That broad pattern remains, yet warming air shifts each stage. One of the clearest changes appears in the snowline, the approximate elevation above which precipitation falls mainly as snow rather than rain during cold season storms. When temperatures rise, this line moves upward. Storms that once spread snow across middle elevations now bring rain there instead. Only the highest slopes remain cold enough to keep the old snowfall pattern. This change matters because rain and snow behave very differently on the land. Snow stores water. Rain moves quickly downslope, enters streams sooner, and leaves less moisture saved for later in the year. The snowpack is the accumulated mass of snow resting on the ground through the cold season. It is not a single layer but a stack built storm by storm, shaped by wind, temperature, and sunlight. In many western mountain systems, the snowpack functions as a natural reservoir. It holds winter moisture in place and releases it gradually as melting begins. Observations indicate that in many areas of the western United States, snowpack has declined over recent decades, especially at lower and middle elevations. This decline does not occur everywhere in the same way every year, but the overall trend reflects warmer winters, more precipitation falling as rain, and earlier snowmelt. Winter itself changes in the mountains before it disappears from them. Snow still falls, deep drifts still form, high ridges still collect wind-driven ice and powder, yet the season grows less stable at its edges. Warm storms interrupt cold periods. Rain falls on existing snow. A thaw settles in midwinter. Then another cold spell follows. These reversals alter the structure of the snowpack. Wet snow may freeze into hard layers. Meltwater may move downward through the pack and refreeze at night. Such changes affect both water storage and avalanche conditions, though the full human consequences belong to later layers. At the climatic level, the main change is a loss of continuity. Winter in the mountains becomes more interrupted. Spring in high country has always been a season of release. Sunlight strengthens, air temperatures rise, and the snow begins to soften, shrink, and retreat upslope. Streams swell with meltwater. South-facing slopes clear first. Meadows emerge in patches. This ordered retreat still occurs, but it often begins earlier than before. Earlier spring warmth starts the melting process sooner, especially at lower elevations. Snow that once remained into late spring vanishes earlier. The boundary between snow-covered and snow-free land climbs higher up the slopes earlier in the year. This earlier melt changes the mountain season in subtle and visible ways. Bare ground absorbs more sunlight than bright snow does. Snow reflects a large share of incoming solar radiation back toward the atmosphere. Darker rock, soil, and vegetation absorb more of that energy and warm more quickly. As the snow cover shrinks, the ground heats faster, which further encourages melting. This is a feedback loop. Reduced snow leads to more warming of the surface. and that warming leads to further snow loss. In this way, the mountains begin to shift from cold seasonal storage toward earlier and stronger warm season heating. The timing of runoff changes with the timing of snowmelt. Water reaches streams earlier, which can leave less available later in summer. But even before that downstream effect becomes visible, the mountains themselves show the altered sequence. Alpine meadows green earlier, wet ground dries sooner. Small snowfields that once lasted into the warm season disappear in early summer. Glaciers, where they still remain in some western ranges, continue to lose mass over long periods because winter snow gain no longer balances summer melt in many places. In the highest terrain, cold persists, but even there the margins retreat. Summer in the mountains has long offered a distinct contrast with the lowlands below. Higher elevations usually remain cooler. Forests cast shade. Streams fed by lingering snow stay cold. Afternoon thunderstorms may build over peaks where rising air reaches condensation level. Yet as snow disappears earlier and temperatures rise, the mountain summer lengthens. Warm ground appears sooner and remains exposed longer. Soils lose moisture over a longer season. Vegetation begins growth earlier but may face water stress before the end of summer. Forests remain under heat for more weeks than they once did. This does not make every mountain summer uniformly hotter in every place. Elevation still provides cooling, and weather still varies greatly from range to range. Yet the larger pattern is one of compression of the cold season and expansion of the warm season. The old mountain calendar depends on the persistence of snow and the delayed arrival of heat. As snow declines and heat arrives earlier, the intervals between one seasonal state and another shorten. The landscape moves more quickly from frozen to thawed, and from thawed to dry. Autumn also changes. In the past, early snow at higher elevations often signaled the clear return of the cold season, even when lower valleys remained mild. Now early snow may still fall, but it may not last. Warm ground and warm air can erase fresh snow quickly below the highest elevations. The visual signal of winter arrives, then retreats. The mountains still cool as day length declines, but the establishment of lasting snow cover may come later. This delays the stable beginning of winter, even while preserving its appearance in brief episodes. Different parts of the western mountains respond differently depending on latitude, altitude, storm exposure, and local geography. Northern ranges and the highest peaks remain colder and may continue to hold substantial snow. Lower mountain zones are more vulnerable because they sit near the threshold, where a small temperature increase changes snow to rain. This threshold behavior is one reason the transformation can feel sudden. The mountain still stands in the same place, but a narrow band of warming is enough to redraw the climate on its slopes. Scientists observe these changes through snow surveys, stream measurements, satellite images, temperature records, and field studies. The broad picture is clear. Many western mountain regions are experiencing declining snowpack, more winter rain, earlier melt, and longer warm seasons. It remains uncertain exactly how each watershed and elevation band will respond in future decades, because storms, local terrain, and natural variability still matter greatly. Even so, the direction of change is visible across much of the high country. The mountains of the American West have long acted as one of the firmest keepers of season, holding winter high above the valleys and releasing it slowly through spring. That role is still present, but it weakens as the cold season shortens, the snow line climbs, and exposed ground returns earlier each year. The mountain calendar remains written in snow, ice, stone, and meltwater, yet the writing grows thinner, less durable, and more easily erased by warmth than it once was. Below the mountain slopes, the seasonal changes in snow and rain gather into moving water. Streams join rivers, rivers enter reservoirs, and entire regions come to depend on the timing of that flow. In the western and central United States, many familiar patterns of spring and summer are shaped not only by how much precipitation falls, but by when frozen water begins to move downhill. For a long time, rivers followed a relatively steady seasonal rhythm. Winter stored moisture in mountain snow. Spring warmth released it in a broad pulse. Early summer carried the remainder through channels, wetlands, and reservoirs. Late summer brought lower water levels and greater dependence on what had already been stored. That rhythm is now changing. The rivers still run, but the seasonal sequence that governs their rise and decline grows less predictable. A river basin is the area of land from which water drains into a common river system. Snow, rain, and groundwater from many elevations and landscapes eventually gather into the same network of channels. In basins fed by mountain snow, the timing of melt is as important as the total amount of winter precipitation. Snow acts as delayed water. It holds moisture in place until warming releases it. When snow melts earlier, water enters streams earlier, and the whole annual pattern of flow begins to shift forward. This earlier runoff appears in stream gauges across many snow-fed watersheds. A stream gauge is a measuring station that records water level and flow. Observations indicate that in many western rivers, the spring peak now arrives earlier than in the past. Instead of a strong rise centered later in spring or early summer, some rivers begin swelling weeks sooner. This does not always mean more total water over the year. In many cases, it means that water moves through the system sooner, leaving less available later in the warm season when demand is high and natural replenishment is low. The shape of the hydrograph changes with this timing. A hydrograph is a record showing how river flow rises and falls over time. In a snow-dominated system, the hydrograph once has a broad spring crest, built from gradual melt at different elevations. Lower slopes begin first, higher slopes later, and the river remains elevated for a sustained period. As warming shifts snow to rain and accelerates melt, this broad crest may flatten, advance, or break into uneven pulses. Warm storms may produce runoff during winter. A sudden thaw may create an early surge. Spring then brings a smaller pulse than expected because part of the stored water has already gone. Rain-fed rivers respond differently from snow-fed rivers, yet they also show seasonal disruption. In places where more winter and spring precipitation now falls as rain, river flow can become flashier. Flashy flow means water levels rise and fall quickly after storms, instead of slow release from snow. Rainfall runs off directly from saturated or frozen ground. The river swells fast, then drops fast. This alters the old seasonal expectation of a stable wet period followed by a stable dry period. The boundary between flood season and low water season becomes less clear. Reservoirs are designed partly to manage this timing. A reservoir stores water behind a dam so that it can be released later for irrigation, drinking water, hydroelectric power, flood control, or environmental needs. In regions with strong snowmelt cycles, reservoir operations have long depended on a seasonal schedule shaped by past river behavior. Managers expect winter inflow, spring rise, peak runoff, and later decline. When runoff comes earlier, the operating rules become harder to balance. Holding too much water before spring can increase flood risk if sudden rain or melt arrives. Releasing too much water early can leave too little for the hotter months ahead. This creates a new tension within the seasonal water system. The old calendar suggests one pattern, but the river increasingly delivers another. Snowmelt arrives before some reservoirs are ready to store it fully. Warm season demand then rises during longer heat, while stream flow may already be dropping. Irrigated agriculture, cities, fish habitat, and electricity generation all rely on timing as much as quantity. The river may still carry substantial water in total. Yet if that water appears at the wrong part of the year, the season feels out of joint. The Colorado River Basin shows this problem in stark form, though similar patterns appear elsewhere. The basin depends heavily on winter mountain snow, and warming reduces the efficiency with which snowfall becomes reliable stream flow. More precipitation falls as rain. More soil moisture is consumed before runoff reaches the channel. More water returns to the atmosphere through evaporation and plant use, even where winter storms remain active. The share of precipitation that survives into reservoir storage can decline. This means the seasonal promise once held by a snowy winter no longer guarantees the same river response downstream. In the Pacific Northwest, California, and parts of the Rocky Mountains, atmospheric rivers add another layer. These narrow corridors of concentrated moisture can deliver intense rainfall or heavy mountain snow, depending on temperature and elevation. When temperatures are lower, such storms help build snowpack. When temperatures are higher, they may send rain onto existing snow. This can accelerate melting and produce large runoff events. Rivers rise quickly. Reservoir managers must respond in real time. The season then behaves less like a slow unfolding and more like a series of difficult adjustments to abrupt pulses. Lower in the basin, floodplains and wetlands register these changes in quieter ways. A floodplain is the flat land beside a river that becomes inundated when water rises beyond the channel. Wetlands depend on the timing, depth, and duration of seasonal water. If spring peaks arrive earlier or become sharper, wetlands may fill and dry on a different schedule. Floodplain forests may receive water at the wrong stage of growth. Fish that depend on cool spring flows may encounter warmer and lower summer water sooner than before. Even without naming later ecological consequences in detail, the river landscape itself shows that the seasonal order has shifted. Summer exposes the new pattern most clearly. In many places, the hot months now arrive with a longer period of low flow ahead of them. Reservoir levels fall under strong demand. Streams run warmer and shallower. Smaller tributaries dry or shrink earlier. Recreation, farming, and water supply all begin to depend more heavily on storage and management rather than on ongoing natural flow. The river still moves through the valley, but it does so with less of the old seasonal support from lingering snow. Autumn offers little automatic correction. In some years, early storms arrive and begin recharge. In others, warmth persists and the channels remain low. Much depends on whether the previous winter built lasting snow and whether spring released it gradually. Because the whole sequence is now less stable. One season carries the imprint of the last. A poor snow year leads into a strained melt season, which leads into a difficult summer, which leaves reservoirs vulnerable before the next winter even begins. Scientists continue to examine how warming, precipitation change, groundwater use, and reservoir operations interact across different basins. Not every river responds in the same way. Local geology, elevation, vegetation, and water management all matter. It remains uncertain how individual watersheds will behave in every future decade. Yet the broad pattern is well supported. In many snow-influenced regions, runoff is shifting earlier, summer low flows are deepening, and the seasonal water calendar is becoming harder to trust. Rivers once translated the mountain year into a long, readable sequence downstream. Snow gathered in silence, melt arrived in order, reservoirs filled on cue, and the dry season followed with a kind of stern predictability. That translation is no longer as clear. Water now moves sooner, faster, or in more uneven pulses. The channels, dams, and storage lakes still bind the landscape together, but the seasonal script they follow has been revised by warmth, and every reach downstream begins to reflect the change. Across the central plains, the land opens wide beneath the sky, and the seasons become visible through motion in the air. This is a region of grasslands, farms, river valleys, and long horizons stretching from Texas northward through Oklahoma, Kansas, Nebraska, and the Dakotas, with nearby transitions into eastern Colorado, eastern New Mexico, and parts of the Midwest. Here the atmosphere meets fewer barriers than in mountainous country. Cold air from the north can move far south. Warm, moist air from the Gulf can surge far inland. Dry air from the high western interior can spread eastward. Because these contrasting air masses meet so directly over the plains, the region has always been one of strong seasonal change. Yet the old rhythm grows less stable. The transitions sharpen, the extremes deepen, and the sequence between one season and the next becomes harder to read. The plains are often described as a meeting ground of air masses. An air mass is a large body of air with broadly similar temperature and moisture characteristics. Over the central United States, continental polar air arrives from Canada with cold and dryness. Maritime tropical air moves north from the Gulf carrying warmth and humidity. Continental tropical air comes from the dry southwest with heat and low moisture. These different bodies of air do not blend smoothly at first contact. They form boundaries, and those boundaries shape wind, clouds, storms, and sudden temperature changes. In the plains, the seasonal year depends heavily on how often and how strongly these air masses collide. Winter still reaches the plains with real force. Cold fronts sweep southward over open ground. Snow falls under passing systems. Bitter wind can spread across the grasslands for days. Yet even in winter, a warmer background climate begins to shift the balance. Some cold outbreaks remain severe, but the average season includes more interruptions by warm air. Chinook winds descend east of the Rocky Mountains in some northern and central areas, briefly raising temperatures with dry, compressed air. Larger-scale warmth also allows some winter thaws to reach farther north or last longer. The result is not the disappearance of winter, but a season that breaks apart more often, alternating between hard cold and episodes of surprising mildness. This pattern affects snow cover, which is one of the key surfaces through which winter expresses itself on the plains. Snow reflects sunlight, insulates the ground, and helps keep near-surface air cold. When snow cover is thin, patchy, or short-lived, the land absorbs more solar energy and warms more quickly during sunny periods. A snow-covered field and a bare field can produce very different local conditions under the same sky. As winters warm and snow becomes less durable in some areas, the cooling effect of snow weakens. The season becomes more vulnerable to rapid changes, especially when warm, dry winds sweep across open terrain. Spring has always been the most dramatic season on the plains because it's the time when the strongest contrasts come together. Southern warmth advances northward, while winter cold still lingers across the continent. Gulf moisture deepens. Dry western air intrudes eastward. These ingredients build instability in the atmosphere. Instability, in simple terms, is a condition in which air that starts rising continues to rise, because it remains warmer than the air around it. Rising air cools. Water vapor condenses and storms develop. Over the plains, this process can produce thunderstorms of extraordinary size and power. That basic pattern remains, but the timing and placement of these ingredients now shift. Spring warmth often arrives earlier than in the past, especially in the southern and central plains. Moist air from the Gulf can surge north earlier in the season as well. Yet cold air still remains available from farther north. This means that the overlap between early warmth and lingering chill can become more erratic. Some periods of spring now accelerate almost directly into summer-like heat, while others swing backward into frost and raw wind. The season does not unfold in a steady climb, it jolts between states. The dry line is one of the most distinctive boundaries of the plains. A dry line is a zone separating moist air from the Gulf and much drier air from the west. Unlike a cold front, it is defined mainly by moisture contrast rather than temperature contrast, though the two often interact. The dry line commonly forms in spring and early summer and serves as a focus for severe thunderstorms. When it sharpens under strong heating, towering clouds may rise along it by late afternoon. In a warmer climate, with changing moisture supply and stronger heat over dry ground, the behavior of the dry line can also change. Its position, strength, and the timing of storm development may shift from historical expectations. This contributes to the impression that familiar storm season arrives in unusual places or at unusual times. The plains also experience large swings in temperature because open land allows rapid movement of air. A powerful front can lower temperatures dramatically within hours. Warm southerly winds can raise them just as quickly. These sudden changes are not new, but as the seasonal background warms, the character of the swings changes. The warm side of the swing becomes hotter. A spring day that might once have reached modest warmth now surges into oppressive heat. An autumn warm spell lasts longer before the next run arrives. Even when cold still appears, it does so against a different baseline. Summer across the plains is increasingly marked by prolonged heat. High-pressure systems can settle over the interior of the continent and remain for days or weeks. Under these systems, skies often stay clear, winds weaken, and temperatures climb. In the southern plains especially, the land may become very dry by early summer if spring rainfall has been limited. Dry soil then reinforces heat because less solar energy is used to evaporate water, and more is used to warm the ground and air. This land-atmosphere feedback is especially powerful in the plains, where broad agricultural fields and grasslands respond directly to moisture conditions. Humidity varies across the region and helps divide its summer character. In the eastern plains, moist air can make heat feel heavy and oppressive. In the western plains, the air may remain drier, but temperatures still become extreme under prolonged sun and wind. The dividing line between humid and dry summer conditions may shift from one week to the next, depending on Gulf flow and pressure patterns. This moving contrast is one reason the plains feel seasonally unstable. The same landscape may experience muggy tropical air, desiccating dry wind, torrential thunderstorm rain, and dusty heat over the course of a short interval. Drought is another defining feature of plain seasonality, and warming strengthens its reach. Drought is a prolonged period of below-normal water availability, usually caused by reduced precipitation, enhanced evaporation, or both. The plains have always been vulnerable to drought because rainfall varies widely from year to year, and much of the region lies near the boundary between humid and semi-arid climates. Now, higher temperatures intensify evaporation from soils and plants. which can deepen drought even when rainfall losses are moderate rather than extreme. A season that appears only somewhat dry in terms of precipitation can feel much drier on the ground because heat extracts moisture so efficiently. When drought combines with wind, the landscape can begin to resemble older memories of dust and exposure. Bare soil becomes vulnerable to erosion, crops suffer stress, pasture growth declines, rivers and farm ponds shrink. Then, when rain finally arrives, it may come in sudden, intense bursts that run off quickly rather than soaking deeply into the ground. This pattern of long, dry intervals punctuated by heavy rainfall is increasingly important across the interior of the country. It means that water arrives less gently and less usefully than seasonal memory expects. Autumn on the plains once offered a clearer easing from summer heat into cooler, drier air. That easing still happens, but often later and less evenly. Warm conditions may persist well into the season, especially in the southern plains, while the northern plains may already see frost and early snow. Strong fronts return more frequently, yet their passage can create sharp shifts rather than a smooth progression. A hot week may be followed by a cold one, then another warm spell, harvest seasons, grassland dormancy, and the return of stable cool weather no longer line up as neatly as they once did. Scientists continue to examine how warming influences severe storms, drought intensity, seasonal temperature swings, and moisture transport across the plains. Some aspects are clearer than others. Observations strongly support the rise in heat, the greater evaporative demand, and the increasing influence of heavy rainfall events. It remains uncertain exactly how some severe storm patterns will change in every part of the region. Because the atmosphere of the plains is shaped by many interacting forces, yet the broader seasonal picture is unmistakable. The central interior is becoming a place of sharper contrasts and less reliable transitions. Over the plains, the seasons have always moved with wind, but now the wind carries stronger imbalance. Cold still descends from the north, warmth still rises from the south, and storms still build where the two meet. Yet the old sequence loosens. Heat stretches longer, drought bites deeper, rainfall arrives harder, and spring and autumn lose part of their steadiness. The open land remains open, but the calendar written in its air no longer reads with the same certainty it once did. Across the fields and forests of America, the changing seasons become visible in living growth. Leaves unfold, stems rise, roots draw water, blossoms open, seeds develop, and wood forms ring by ring beneath bark. These processes do not follow the calendar in a human sense. They respond to light, temperature, moisture, and chemical signals shaped by the atmosphere and the soil. For a long time, those signals arrive in patterns stable enough to support a recognizable yearly cycle. Spring warmth comes after winter chill, summer heat builds after new growth has begun, autumn cooling slows activity and prepares plants for dormancy. Winter then holds many systems in rest. That broad order still exists, but its timing and balance are changing. In fields, orchards, grasslands, and forests, the growing season now stretches, stumbles, and strains in ways that reveal how deeply the seasons themselves are shifting. A growing season is the part of the year during which temperatures and moisture allow plants to grow actively in colder regions. It begins after the danger of sustained freezing has passed and ends when autumn cold returns. In warmer regions, growth may continue through much of the year, though its pace still varies by season. Observations indicate that in many parts of the United States, the growing season has lengthened over recent decades. Spring warmth often arrives earlier. and the first autumn frost often comes later. On the surface, this might seem like a simple expansion of opportunity for plants, yet living systems depend not only on longer warmth, but on the right sequence of events. Winter chill is one of the first parts of that sequence. Many plants, especially trees and shrubs in temperate climates, require a period of cool or cold conditions before they can resume normal growth in spring. This prevents them from responding too early to brief warm spells in midwinter. When winters become milder, some plants receive less of this chill. In certain fruit trees, for example, reduced chill can delay or unevenly trigger flowering and leaf emergence. The season still turns towards spring, but the biological clock of the plant may no longer align as cleanly with the changing air. When warm periods arrive earlier, many plants begin growth sooner. Buds swell, leaves appear, blossoms open, fields green earlier than they once did. This early activity creates the appearance of a longer, more generous spring. Yet the warmth that begins growth is not always followed by steady safety. Late frosts still occur in many regions. A late frost is a freezing event that happens after plants have already resumed spring growth. Tender tissues that emerge early are especially vulnerable. Blossoms blacken, new leaves wilt, young stems suffer damage. In this way, an earlier spring can increase rather than reduce risk, because the season invites growth before the atmosphere has finished delivering cold. This mismatch appears clearly in orchards and vineyards, where timing matters with unusual precision. Fruit trees rely on a sequence of winter chill, spring warming, pollination, fruit development, and summer ripening. A sudden warm spell in late winter may trigger bloom, only for a freeze to arrive days later. Entire harvests can be reduced or lost in a single night. Similar patterns affect berries, nuts, and other perennial crops. The season is no longer only warmer. It becomes less reliable in the order of its signals. Row crops across the United States also respond to these altered seasons. Corn, soybean, wheat, and many other crops depend on soil temperature, rainfall timing, day length, and summer heat. Longer frost-free periods can permit earlier planting in some regions or allow cultivation of crops farther north than before. Yet higher temperatures also increase water demand. Heat during sensitive stages such as pollination or grain filling can reduce yields. Heavy rain at the wrong time can delay planting, erode soil, or waterlog roots. Dry spells between intense storms can stress crops even in seasons with near normal total rainfall. The problem is not only how much weather arrives, it is whether it arrives in the order plants can use. Soil plays a central role in this changing seasonal story. Soil stores water, nutrients, air, and organic matter. It also buffers plants against short-term swings in weather. When spring arrives earlier and temperatures rise faster, soils may warm sooner, but they may also dry sooner. Dry soil supports less plant growth and amplifies heat because less energy goes into evaporation. During heavy rainfall, dry or compacted soil may fail to absorb water efficiently, allowing runoff to carry moisture and topsoil away. This creates a season in which both dryness and flooding can occur within the same landscape, sometimes within the same month. Grasslands reveal the shift in a quieter way. Native grasses respond closely to temperature and moisture timing. Earlier warmth may prompt earlier green-up, but prolonged heat and altered rainfall can shorten the period of active growth. In some regions, cool-season grasses lose ground under hotter summers, while warm-season grasses expand. This changes the texture and productivity of pastures and prairies. It also alters when forage is available for livestock and wildlife. The land may still turn green each year, but the timing, duration, and composition of that greenness shift. Forests hold a longer memory of seasonal change because trees grow slowly and remain in place for decades or centuries. Spring leaf out has advanced in many temperate forests, and autumn leaf drop in some regions occurs later than before. This extends the period in which leaves are active, drawing in carbon dioxide and using sunlight to build tissue. In some cases, this can increase annual growth, especially where water remains sufficient and heat stays moderate. But extended growing seasons also expose forests to longer periods of moisture stress, pest activity, and heat strain. Trees do not benefit from longer warmth if that warmth is accompanied by drought or repeated extremes. Different tree species respond differently. Some take advantage of earlier warmth, others remain more closely tied to day length and do not advance as quickly. Day length, unlike temperature, does not change from year to year. The amount of daylight on a given date is fixed by the motion of the Earth. This means that some seasonal cues are shifting while others remain constant. Plants that depend strongly on temperature may move their schedule forward. Plants that depend more on light may hold their old timing longer. This divergence changes the internal rhythm of forests. Species that once leafed out together may now do so further apart in time. Autumn in fields and forests changes as well. Later frosts and warmer conditions can delay dormancy, the resting state in which growth slows or stops. Crops may mature later. Trees may hold green leaves longer into the season. Yet a warm autumn does not always provide a healthy extension. If moisture is limited, plants may shut down early from drought stress even while temperatures remain high. Leaves may brown rather than turn gradually. Grass may cure and dry rather than continue growing. Thus, autumn can become a strange season in which warmth lingers, but living growth does not fully follow it. Wildfire leaves a growing mark on forests and rangelands in some regions, especially where hotter seasons dry vegetation for longer periods. Fire belongs to certain ecosystems as a natural process, but longer heat, earlier snowmelt, and drier fuels can lengthen the period during which large fires are possible. This changes the seasonal structure of the landscape itself. A forest once shaped by snowmelt spring and moderate summer may now face months of drying before the first autumn moisture returns. Researchers study these changes through field observations, tree rings, satellite imagery, crop records, and long-term measurements of flowering and leaf out. The evidence shows that plant seasons are shifting across the country, though not always in the same direction or at the same pace. It remains uncertain how each region and species combination will respond over the coming decades, because soil, water, genetics, and management all influence the result. Yet the larger pattern is clear. The living surface of the land is no longer receiving the same seasonal sequence it evolved with or adapted to in recent history. In America's fields and forests, the year still unfolds through bud, leaf, flower, fruit, seed, and rest. But the intervals between these stages are changing. Spring begins earlier, yet remains vulnerable. Summer grows longer, yet more stressful. Autumn stays warmer, yet less dependable as a season of steady easing. The land continues to grow, but it does so under a calendar whose signals are increasingly out of order, and that disorder is written plainly in every field that greens too soon, every orchard struck by late frost, and every forest that holds its leaves into a warmth that no longer feels like the old season. Beyond the visible timing of leaves and crops, the changing seasons reach into the lives of animals whose yearly patterns depend on temperature, light, moisture, and food. Insects emerge from soil, bark, or water at particular times. Birds migrate over long distances toward breeding grounds timed to spring abundance. Pollinators seek flowers when nectar and pollen are available. Mammals breed, molt, store fat, or change behavior according to seasonal cues that were once reliable enough to support survival across generations. These patterns still continue, but many are beginning to fall out of step. The season does not vanish for these animals. Instead, the signals arrive in altered order, with warmth advancing ahead of food in one place, or food shifting ahead of migration in another. What appears from a distance to be a simple early spring or delayed autumn becomes, at the level of animal life, a growing problem of timing. Phenology is the study of seasonal timing in living things. It examines when birds arrive, when insects hatch, when plants flower, and when animals breed or hibernate. For many species, success depends not only on being active during the right part of the year, but on matching that activity to the timing of other species. A pollinator must arrive when flowers are open. A bird that feeds its young on caterpillars must nest when caterpillars are abundant. A bat that emerges from winter torpor must do so when insects are flying. When different parts of this living calendar shift at different rates, mismatch appears. A mismatch happens when two species or two linked seasonal events no longer line up in time as they once did. The most widely observed examples involve spring. Warmer temperatures can cause plants to leaf out or flower earlier. Some insects also emerge earlier because their development depends strongly on heat. But not all animals respond to the same cue. Many migrating birds use day length as a major signal for departure and movement. Day length does not change from year to year. It remains fixed by the motion of the Earth around the Sun. This means that a bird may begin migration according to the old light schedule, even while the spring conditions at its destination are already shifting forward. When such a bird arrives, the peak abundance of the food it needs may already have passed. In forest ecosystems, for example, some birds depend on a short spring pulse of caterpillars that feed on newly unfolded leaves. If leaves open earlier because of warmth, and caterpillars reach peak numbers earlier as a result, birds that arrive on their usual schedule may miss the richest feeding period. They may still breed, but with less food available for chicks at the most important moment. The season therefore remains present, yet its internal coordination weakens. Insects respond quickly to changing temperature because many of them are small and develop rapidly. Warmer springs can speed their growth and bring earlier emergence. Warmer winters can also increase survival for some species by reducing exposure to prolonged freezing. This is especially important in regions where cold once limited the range or seasonal activity of pests. In some parts of the United States, insects now remain active longer into autumn or begin activity earlier in spring. Some may even produce more generations in a single warm season than they once did. A generation is one full life cycle from egg to reproducing adult. When the warm season lengthens, certain species can fit more of these cycles into the year. This change matters not only for crops and forests but for the wider ecological fabric. Insects are pollinators, decomposers, prey, and in some cases disease carriers. When their season lengthens or shifts, everything linked to them feels the effect. Pollinators may appear before or after the flowering peak of some plants. Pest outbreaks may expand into times of year that once remained relatively quiet. Birds and amphibians that feed on insects may find abundance increased in one period and reduced in another. The old rhythm of spring emergence and autumn decline becomes less consistent. Butterflies provide one example of how sensitive these seasonal links can be. Many species time their life stages around the availability of specific host plants, which are the plants their larvae must eat. If plants leaf out or dry out earlier under warmer conditions, the window during which larvae can feed may shift. Adult butterflies may emerge earlier as well, but not always in perfect coordination with nectar sources or weather conditions needed for movement and reproduction. A warmer season can therefore create both opportunity and risk. It may lengthen activity, but it can also expose delicate life stages to heat, drought, or untimely storms. Bird migration reveals the problem over long distances. Many birds winter far south of the United States and travel north in spring to breed. Along the way, they depend on stopover habitats where food is available at the right time. If warming changes conditions differently across the route, birds may face a sequence of altered stages rather than one simple shift. Wetlands may dry earlier, insect emergence may peak sooner, strong storms may occur during migration periods in new ways. By the time birds reach breeding grounds, the season they have tracked for generations may no longer be arranged as before. Not all species respond in the same way. Some birds have shown advances in migration or breeding dates. Others have changed little. Some resident birds, which remain in the same region year-round, can respond more flexibly to local temperature and food conditions. Migratory species may face greater difficulty if they depend on fixed cues from far away. The result is a growing unevenness among species that once moved through spring together. One arrives early, another late. Another on time for the old season, but late for the new one. Aquatic insects and amphibians also depend on seasonal timing, snowmelt, stream temperature, pond filling, and rainfall influence when eggs hatch and larvae develop. Earlier runoff and warmer water can shift these schedules. Vernal pools, which are temporary spring pools that support breeding by frogs, salamanders, and many invertebrates, may fill earlier and dry sooner. If larvae do not complete development before the water disappears, breeding success falls. Here again, the issue is not only warmth, it is the changed order of moisture, heat, and duration. Some animals benefit for a time from longer warm seasons. Certain birds may find a longer breeding period. Some insects may expand northward. Mild winters may reduce cold stress for species once limited by freezing temperatures. Yet these gains are uneven and often temporary. A longer season can also mean longer exposure to predators, parasites, drought, smoke, or extreme heat. What expands at one edge of the year may become more fragile at another. Autumn brings its own mismatches. Migrating birds often depart according to day length, yet the insects, seeds, and fruits they rely on may persist longer or disappear earlier depending on drought and heat. Hibernating mammals may enter winter quarters during a period that remains unusually warm. Insects may stay active later, which can affect disease transmission, forest health, and food webs. The decline into winter no longer happens with the same clear pace, and species that evolved under a steadier descent must now navigate a season that hesitates, reverses, or stretches. Scientists track these changes through bird counts, insect monitoring, flowering records, radar studies of migration, and long-term ecological research. The evidence shows that seasonal timing is shifting across many groups of organisms, but not uniformly. It remains uncertain which species will adapt successfully and which will struggle most in each region, because responses depend on mobility, lifespan, food specialization, and habitat condition. Even so, the pattern of growing mismatch is already clear in many ecosystems. Across America, the altered seasons do not simply warm the air or move the frost. They disturb the coordination between species that depend on one another's timing. Insects hatch under a different schedule. Birds arrive to change landscapes. Pollinators and blossoms no longer meet as reliably. The living year continues, but its parts no longer enter in the same order, and that quiet disorder spreads through woods. wetlands, fields, and skies with every season that slips further from its old arrangement. Around the inland waters of the upper Midwest and Northeast, the seasons have long been shaped by the mass and memory of the Great Lakes. Superior, Michigan, Huron, Erie, and Ontario do not behave like ordinary lakes. Their size allows them to store vast amounts of heat in warm months and release that heat slowly as the air cools. In winter they can remain warmer than the surrounding land, softening cold near the shore and feeding snow clouds when bitter air moves across them. In spring they often remain colder than the land, delaying warmth along the coast and holding back the advance of leaf-out and planting. This steady exchange between water and air has made the Great Lakes one of the most distinctive seasonal engines in North America. Yet that engine is changing. The lakes still shape the year, but their water is warming, their winter ice is diminishing, and the old rhythm of cold, snow, thaw, and summer moderation is becoming less stable. Water changes temperature more slowly than land because it takes more energy to warm it and more energy to cool it. The Great Lakes therefore act as large thermal reservoirs. In autumn and early winter, they give off heat that has built up during summer. In late spring and early summer, they remain cool while nearby land has already warmed strongly. This contrast affects wind, cloud formation, shoreline temperature, and the timing of growing seasons. Places close to the lakes often experience cooler springs, milder autumns, and distinct local weather compared with areas only a short distance inland. These effects remain, but they now occur within a warmer background climate. Lake surface temperatures have risen over time, especially during warm months and in years with reduced winter ice. A warmer lake enters autumn with more stored heat. This can delay the onset of colder shoreline conditions and extend the mildness of early winter near the water. Yet this stored warmth also influences evaporation, cloud formation, and storm development. More heat in the lake can mean more moisture moving into the atmosphere when cold air passes over the open surface. The result is not a simple weakening of winter. Instead, the season changes in character. Winter ice is one of the clearest markers of this change. Ice cover on the Great Lakes forms when cold air removes enough heat from the water surface for freezing to begin. Ice then alters the exchange between lake and atmosphere. It reduces evaporation, limits wave action, and cuts off much of the direct moisture supply to the air above. In many winters of the past, broad areas of the lakes developed substantial ice cover, especially on shallower lakes and in sheltered bays. Observations indicate that long-term ice cover has declined across the Great Lakes, though it still varies greatly from one winter to another depending on air temperature, wind, and storm patterns. This decline matters because open water and ice-covered water behave very differently in the cold season. Open water continues to release heat and moisture. Ice-covered water is more sealed off from the atmosphere. When more of the lake remains open during winter, nearby air can stay milder, and the boundary between lake and land becomes more active. The lakes continue breathing heat into the season for longer than they once did, along some shorelines. This can reduce the persistence of deep cold, yet under the right conditions, it can also intensify snowfall. Lake effect snow forms when cold, dry air moves across relatively warmer lake water. The air picks up heat and moisture from the surface. As it travels downwind and reaches land, it rises, cools, and condenses into cloud and snow. This process can produce narrow but powerful bands of snowfall, especially east and southeast of the lakes where prevailing winds often carry the air. Lake effect snow has always been one of the defining winter features of the region. What changes now is the balance between open water, air temperature, and freezing conditions. In a moderately cold winter, reduced ice can allow more open water to feed lake-effect snow for longer parts of the season. This means some snowstorms can become more intense even as the overall climate warms. But if winter temperatures rise too much, precipitation increasingly falls as rain rather than snow, especially near the lake shores and during the early and late parts of the cold season. Thus, the region may experience a strange combination: shorter periods of lasting snow cover, more winter rain, and yet occasional bursts of very heavy lake-effect snow when cold air crosses open water. The season remains winter, but its structure grows more uneven. Snow cover on the ground also becomes less reliable in many parts of the Great Lakes region. A snowpack may build after a storm, then melt during a mild spell, then return with another outbreak of cold. These interruptions matter because snow cover helps maintain winter conditions by reflecting sunlight and insulating the ground. When snow comes and goes repeatedly, the land moves in and out of winter rather than settling into it. Fields darken, absorb sunlight, and warm during thaw periods. Streams respond to meltwater in midwinter. Shoreline towns cycle between frozen and wet conditions. The visual and physical continuity of the season weakens. Spring around the Great Lakes has always arrived slowly. The lakes remain cold after winter, and onshore winds carry that chill inland. This delays budding, planting, and beach warming near the coast. Inland areas may move ahead into spring while shoreline communities remain under cool grey skies and cold breezes. That pattern still holds, but warmer winters and lower ice cover can alter how the lakes enter spring. Earlier loss of ice exposes more open water to wind and sunlight. Surface layers begin to mix sooner under certain conditions. In some areas, shoreline spring remains cool, yet the broader seasonal contrast between frozen winter lake and thawing spring lake becomes less sharp than before. Summer also changes because warmer lakes do not moderate heat in exactly the same way. The lakes still cool adjacent shorelines relative to inland heat, especially when breezes blow from water to land. But if the water itself is warmer than in earlier decades, that cooling influence weakens somewhat. Warm nights near the shore may become more common. Humidity can remain higher. The shoreline climate still differs from inland areas, but the distinction can narrow during some parts of the season. This contributes to the sense that even the lakes, once such powerful keepers of seasonal order, are no longer producing the same familiar signals. Autumn may be one of the most visibly altered seasons in the region. The lakes release summer heat slowly, and with warmer water they can hold on to that heat even longer. Coastal areas remain mild later into the year. First frosts may be delayed near the shore. Trees may hold leaves longer in some zones. Yet at the same time, warm lake water can add energy and moisture to passing storm systems, supporting heavy rain and strong wind under the right conditions. Autumn then becomes both softer and more volatile, less a gentle decline and more an unstable season of lingering warmth punctuated by intense weather. The Great Lakes also influence fog, cloudiness, shoreline erosion, and wave activity, all of which carry seasonal implications. Reduced ice leaves winter shorelines more exposed to waves and storm-driven water movement. Heavy autumn and winter storms can therefore act on coasts that once would have been partially protected by shorefast ice, which is ice attached to the shore. Beaches, bluffs, and harbour edges feel this change directly. The seasonal shield of ice arrives later, forms less completely or fails to persist. Scientists study these patterns through satellite images, buoy measurements, ice records, shoreline observations, and regional climate models. The overall picture is clear. The Great Lakes are warming, long-term ice cover is declining, and the lake-shaped seasons of the surrounding states and provinces are shifting. it remains uncertain exactly how each lake basin and shoreline community will experience future combinations of open water, snow, rain, and storminess. Because wind patterns and year-to-year variability still matter greatly, yet the direction of change is already visible in the altered winter and shoulder seasons of the region. The Great Lakes once gave the interior East a strong and recognizable seasonal cadence. They delayed spring, deepened some snow belts, softened autumn, and marked winter with ice that spread like a second horizon across the water. They still perform these roles, but with increasing irregularity. Open water lasts longer, ice retreats, snow comes in more uneven bursts, and the boundary between rain and snow shifts more often toward rain. In this inland water world, the seasons still gather and disperse around the lakes, but the old balance between cold surface, frozen shore, and patient thaw is steadily giving way to a warmer and less predictable rhythm. Inside American cities, the shifting seasons meet stone, glass, steel, asphalt, and concrete. The natural cycle of warming and cooling still moves through urban areas, but it does so after passing across surfaces that absorb, hold, and release heat in ways very different from forests, grasslands, wetlands, or open soil. Because of this, cities do not merely experience the changing seasons, they reshape them. A spring day warms faster over pavement than over moist ground. A summer night cools more slowly between buildings than over open fields. Autumn lingers in retained heat, and winter cold is softened or interrupted by the stored warmth of the built environment. As the broader climate warms, this urban influence becomes stronger, and many city dwellers come to feel that the old seasonal calendar has not only changed, but become artificial. The urban heat island is one of the central terms for this process. It refers to the tendency for cities to remain warmer than nearby rural areas, especially at night. This happens for several reasons. Buildings and roads often have dark surfaces that absorb solar energy efficiently. These materials store heat during the day and release it slowly after sunset. Cities also contain less vegetation and exposed soil, which means less cooling through shade and evaporation. Vehicles, air conditioners, industrial activity, and dense patterns of human energy use add further warmth. The result is a local climate within the larger regional one, and this local climate changes how each season is lived. Spring in cities often seems to begin early. Pavement clears quickly after snow or frost. South-facing walls absorb sunlight and warm the surrounding air. Trees planted along streets may leaf out sooner than the same species in cooler outskirts. Ornamental plants in parks and yards respond to slightly elevated night temperatures. These early signs can make the city appear to enter spring ahead of the countryside. Yet the early shift is not always stable. Cold air still arrives with fronts, and a brief return to winter can still damage new growth. What changes is that the urban environment encourages early warming and compresses the boundary between late winter and spring. This effect becomes strongest at night. In rural landscapes, open ground and vegetation can radiate heat away efficiently under clear skies. In cities, walls, roofs, and roads continue releasing the heat they stored through the day. The geometry of streets can also trap warmth by limiting how efficiently surfaces lose heat to the open sky. Spring nights that once dipped low enough to produce widespread frost may now remain just warm enough in city centres to avoid it. This small difference changes flowering times, insect activity, and the timing of outdoor life. It also contributes to the broader feeling that the season arrives earlier and with less hesitation. Summer brings the most powerful expression of artificial seasonality in cities. Heat enters the built environment and lingers there, asphalt softens in sun. Concrete walls radiate stored warmth into the evening. Air conditioners remove heat from indoors and expel it outside, making streets and alleys warmer still. In dense neighborhoods with limited tree cover, the warm season becomes concentrated and persistent. It does not end at sunset in the same way it might in greener or more open surroundings. The city creates its own continuation of summer through the night. This nighttime persistence matters more than many daytime measurements suggest. When nights remain warm, people recover less effectively from daytime heat. Homes without sufficient cooling retain warmth. Transit systems, power lines, and water systems operate under greater strain. The season becomes more exhausting because it occupies the full daily cycle. In a warming national climate, the urban heat island pushes cities further toward longer stretches of oppressive conditions. A regional heatwave becomes an even more severe city event because the built environment intensifies and prolongs it. Humidity and stormwater add another layer to this altered season. Rain that falls on forests or open ground can infiltrate soil, evaporate from leaves, or move slowly through wetlands and streams. In cities, much of the surface is impervious, meaning water cannot easily soak in. Streets, roofs, parking lots, and sidewalks send rainfall quickly into drains or low-lying areas. When warmer air supports heavier downpours, urban areas often experience flash flooding. The seasonal rain pattern therefore changes in character. A summer storm that might once have been inconvenient becomes dangerous because it falls on hardened surfaces that accelerate runoff. The lack of vegetation also changes the texture of each season. Trees cool the air through shade and transpiration, which is the release of water vapor from leaves. Parks and green corridors create pockets of cooler air and slower warming. Where those features are absent, seasonal transitions become harsher. Spring jumps quickly into heat. Summer deepens without relief. Autumn remains warm in paved districts long after surrounding landscapes cool. Winter, though still present, can feel reduced to short episodes between mild spells, especially in the downtown cores of large cities. The names of the seasons remain, but the sensory experience becomes increasingly dominated by infrastructure. Autumn in cities often carries a strange delay. Day length shortens, leaves begin to colour, and the sun's angle lowers. Yet heat stored in the built fabric slows the feeling of seasonal descent. Outdoor dining, traffic, construction, and late warm evenings continue far into the year. Street trees may hold leaves later than trees in nearby rural zones because overnight temperatures remain slightly higher. Buildings release accumulated summer heat, and the first real cool spells often feel postponed. When cold air does arrive, it may be sharp and sudden, producing a stronger contrast than the more gradual autumn of less built landscapes. Winter shows the urban transformation in a quieter way. Snow that falls in cities is often disrupted quickly by traffic, salt, mechanical clearing, and warmer pavement. Slush replaces lasting snow cover. Rooftops drip during sunny hours. Roads remain wet rather than frozen under conditions that might preserve snow in surrounding areas. The urban heat island cannot prevent winter, especially during major cold outbreaks, but it can erode its continuity. Instead of a stable cold season with persistent snow cover, many cities experience repeated oscillation between snow, melt, refreeze, and bare pavement. Winter becomes fragmented. Air quality also interacts with these altered urban seasons. Heat can worsen ozone formation in summer. Stagnant air under high pressure can trap pollutants near the surface. Smoke from distant wildfires may settle over cities during hot months. turning the season not only warmer but more difficult to breathe. In winter, temperature inversions in some cities trap cold air and pollutants near the ground. These patterns are not new, but they become more significant as warmer seasons lengthen and atmospheric extremes become more common. The city season is therefore shaped not only by temperature, but by what the air carries and how long it remains trapped among buildings. Human design choices can either intensify or soften these changes. Tree planting, reflective roofing, permeable surfaces, shaded streets, urban wetlands, and better building design can reduce heat accumulation and improve drainage. Dense neighborhoods with little vegetation and large expanses of dark pavement tend to amplify artificial seasonality. Greener districts create more moderation. This means the seasonal experience of a city is not uniform even within the same metropolitan area. One neighborhood may hold heat far into the night while another cools beneath trees and open ground. The urban season is therefore patterned not only by climate, but by inequality in land cover, design, and infrastructure. Scientists study city climates with ground sensors, satellites, building data, and temperature mapping conducted block by block. Their findings consistently show that urban heat islands raise temperatures, especially nighttime temperatures, and that this effect interacts with the broader warming climate. It remains uncertain exactly how each city will evolve as architecture, land use, and adaptation measures change, but the present pattern is well established. Cities modify the timing and feeling of every season, and that modification grows more pronounced as the underlying climate warms. In urban America, the changing seasons are filtered through the materials of modern life. Heat gathers in pavement, lingers in walls, runs off rooftops, and glows back into the evening air. Spring arrives early but uncertain. Summer expands and refuses to release the night. Autumn cools reluctantly. Winter comes in fragments, often interrupted by thaw and exposed concrete. The city does not erase the seasons, but it remakes them into something harder, hotter, and less natural in rhythm, until the old progression of the year begins to feel less like a cycle of nature and more like a climate engineered by the surfaces people have laid across the land. Within human life, the changing seasons are felt not only in weather records or landscapes, but in the body's own timing, habits, and memory. People sleep differently in heat than in cold. They move through the day according to light, temperature, pollen, rain, and wind. Work follows seasonal assumptions about safe outdoor hours, planting and harvest windows, school calendars, travel, heating, cooling, and the rise and fall of illness. Culture builds its own rhythm around these recurring patterns. Clothing, food, festivals, labor, migration, recreation, and rest all come to depend on a rough trust that spring will resemble spring. Summer will remain within known limits. Autumn will cool in due course, and winter will arrive with its own steadier demands. That trust weakens when the seasons begin arriving out of sequence or with unfamiliar force. The human body notices, and so does collective memory. The body depends on regulation of temperature within a narrow range. Sweating, shivering, blood flow, thirst, and hormonal responses all help maintain internal stability as the external environment changes. In cooler conditions, blood vessels near the skin narrow to reduce heat loss, and the body may begin to shiver to generate warmth through muscle activity. In hotter conditions, blood flow to the skin increases and sweat evaporates to carry heat away. These responses work best when the surrounding environment allows them to work. When heat becomes too intense, humidity too high, or warm nights too persistent, the margin of safety narrows. The season then becomes more than a backdrop. It becomes a physical load carried by every organ system. Warm nights are especially important because sleep is part of how the body recovers from heat. During sleep, internal temperature normally declines slightly, helping rest deepen and repair proceed, when bedroom air remains warm, or when urban heat and humidity prevent cooling after sunset. Sleep becomes lighter and more fragmented. People wake more often, perspire more, and begin the next day less restored. If this pattern continues over days or weeks, the season of heat no longer consists only of hot afternoons. It spreads into the full cycle of living, altering mood, concentration, appetite, and endurance. Older adults, infants, outdoor workers, and people with chronic illness often face greater seasonal stress because the body's ability to regulate heat or respond to rapid change may be reduced. Yet even healthy adults feel the broad shift. A spring that swings sharply from warmth to cold affects energy use, clothing, transport, and work schedules. A summer that extends longer than expected increases cumulative strain. Autumn that stays warm while pollen remains active extends allergy symptoms and delays the body's sensory sense of seasonal change. Winter that arrives in brief hard bursts between long, mild spells may feel more disorienting than a steady cold season once did. Pollen is one of the clearest ways altered seasons enter the body. Many trees release pollen in spring, grasses in late spring and summer, and ragweed and related plants in late summer and autumn. When warmer conditions begin earlier, flowering can begin earlier as well. When frost arrives later, pollen-producing plants may remain active longer. This extends the period during which sensitive people experience nasal inflammation, eye irritation, coughing, and fatigue. The season of allergy grows longer not because pollen changes its nature, but because the climate shifts the boundaries within which pollen is present in the air. Smoke has also become a more frequent seasonal burden in some parts of the United States. Large wildfires send fine particles into the atmosphere, and winds may carry them far from the burn area. These particles can enter deep into the lungs and worsen asthma, heart disease, and general respiratory stress, in regions once defined by a dry summer but not by prolonged smoke. The warm season now includes days or weeks of muted sunlight and poor air quality. The season therefore changes in memory as well as in measurement. Summer is no longer recalled only through heat, insects, and long evenings. It may also be remembered through haze, warnings, and the taste of smoke. Human routines depend heavily on seasonal expectation. Schools open and close according to old assumptions about heat, storms, and winter conditions. Construction, road repair, shipping, tourism, and agriculture are all organized around calendars built from historical averages. When spring floods arrive earlier, when summer heat becomes dangerous for longer parts of the day, or when winter storms shift toward heavy rain and ice rather than dependable snow, those routines strain. Outdoor labor becomes harder to schedule. Utility systems face longer cooling demand and irregular heating demand. Insurance, travel, and emergency response all begin operating under seasons that still bear familiar names but less familiar behavior. The emotional and cultural side of season matters as well. Human memory relies on repetition. Repeated patterns teach people what time of year it is supposed to feel like. Autumn is associated with crisp air, lowering light, and a clean retreat from summer heat. Winter is associated with stillness, hard ground, and a settled cold. Spring is associated with reliable renewal after the last freeze. When those sensory markers blur, memory itself begins to lose a stable anchor. A hot day in late autumn or a wave of flowering before the end of winter may seem at first like a curiosity. repeated over years. It becomes a form of quiet estrangement. The body recognizes the light and the calendar, yet the air does not match the expected season. This mismatch affects mental life in subtle ways. Seasonal habits help structure anticipation and recovery. People prepare for summer, endure winter, and look forward to spring under assumptions formed by long experience. When heat lingers into months that once brought relief, or when sudden cold interrupts an early warm period, that expectation is broken. This does not create a single universal emotional response, because people differ by region, age, work, and preference. Still, a broader uncertainty enters the relationship between people and the year itself. The season becomes harder to inhabit with confidence. Health risks also move with the altered calendar. Heat-related illness now threatens earlier in the year in some regions, before people have fully adjusted their routines or their buildings. Mosquito and tick activity may extend longer where warmth persists, increasing the seasonal window for some diseases. Heavy rainfall can contaminate water systems or promote mold in homes after flooding. Winter that oscillates around freezing increases slip hazards, transportation disruption, and infrastructure damage in ways different from stable cold. In each case, the issue is not simply more of one season or less of another. It is the instability of the transitions and the lengthening of exposure. Indoor environments reveal another layer of this changed relationship. Buildings in many parts of the United States are designed according to local seasonal norms. Insulation, ventilation, heating systems, and cooling systems all reflect expectations about the typical year. As summers lengthen and heat intensifies, some homes become unsafe without cooling. As winters become more erratic, energy demand becomes harder to predict. A household may need air conditioning sooner in spring, use it deep into autumn, then still require brief intense heating during sudden winter outbreaks. The domestic year becomes less legible. Thermostats, utility bills, and patterns of open windows and sealed rooms no longer follow the old sequence. Children absorb these changes through experience before they understand them in science. Snow days become less frequent in some places and more chaotic in others. School sports face heat cancellation. The first signs of spring come earlier, but so do some storms, insects, and smoke days. Seasonal memory, which once passed quietly from one generation to the next through repeated local patterns, begins to diverge. Older people recall a steadier order. Younger people inherit a shifting one. Both live under the same sky, but the meaning of the seasons in lived experience begins to separate across generations. Researchers studying health, labor, sleep, allergy, and climate adaptation find growing evidence that altered seasons are affecting the body and social life together. The effects vary by region and circumstance, and it remains uncertain how quickly communities will adapt their buildings, schedules, and public health systems to these changes. Yet the present pattern is already clear. The human experience of season is no longer only a matter of tradition or personal impression. It is increasingly shaped by measurable shifts in heat, air quality, biological timing, and environmental instability. In daily life across America, the seasons are no longer simply observed. They are absorbed into skin, lungs, sleep, work, and memory under new conditions. Spring begins sooner but cannot always be trusted. Summer stretches beyond its old limits and follows people into the night. Autumn loses part of its cooling promise. Winter arrives less steadily, sometimes softer, sometimes more abrupt. The body continues to adapt as it always has, but the year pressing against it now behaves with less order than the generations before had learned to expect. and that loss of order settles quietly into the most ordinary parts of being alive. At the innermost level of this changing pattern, the altered seasons in America begin with energy. The Earth receives energy from the Sun in the form of incoming radiation. Some of that energy is reflected back to space by clouds, ice, bright land surfaces, and the atmosphere itself. The rest is absorbed by the land, the oceans, and the air. The planet then releases energy back outward in the form of infrared radiation, which is heat emitted from the surface and atmosphere. For long stretches of human history, this balance remains close enough to stable that the broad pattern of climate changes only slowly. Seasons vary from year to year, but they do so within limits shaped by a relatively steady planetary energy system. That system is now under strain because more heat is being retained than released. The main reason is the rising concentration of greenhouse gases in the atmosphere. Greenhouse gases include carbon dioxide, methane, nitrous oxide, and several industrial gases present in smaller amounts. These gases allow most incoming sunlight to pass through the atmosphere, but they absorb part of the infrared radiation the Earth tries to send back into space. After absorbing that energy, they re-emit it in different directions, including back toward the surface. This slows the loss of heat from the lower atmosphere and surface. The process is known as the greenhouse effect. It is a natural feature of the Earth system, and without it the planet would be far colder. What changes in the modern era is the strength of the effect. Human activity adds greenhouse gases faster than natural systems can remove them, and this deepens the atmospheric hold on heat. Carbon dioxide is the largest driver of a long-term warming because it is released in very large amounts through the burning of coal, oil, and natural gas, as well as through deforestation and certain industrial processes. Methane is present in smaller concentration but traps much more heat per molecule over shorter periods, and it comes from sources such as fossil fuel systems, agriculture, and waste. Nitrous oxide also contributes, especially from agricultural soils and industry. Together, these gases change the composition of the atmosphere enough to affect the whole climate system. The result is an energy imbalance. More energy enters and remains within the Earth system than leaves it. The extra heat does not stay in one place. Most of it enters the oceans, but substantial effects also appear in the air, on land, in ice, and in the water cycle. This added heat does not create a new season. It alters the old ones from within. Winter becomes milder on average because fewer cold conditions are able to persist against a warmer background. Spring begins earlier in many places because temperatures cross biological and physical thresholds sooner than before. Summer expands because warm conditions arrive sooner and depart later. Autumn delays its cooling because the atmosphere, land, and water have all stored more heat through the year and release it more slowly. These changes do not happen evenly across all regions because the energy imbalance interacts with geography, circulation, topography, vegetation, and water. But the underlying cause is shared. The seasonal cycle now unfolds in a climate system carrying extra retained heat. The water cycle amplifies this shift. As temperatures rise, evaporation increases from oceans, lakes, soils, and vegetation. Warmer air can hold more water vapor, and water vapor is itself a greenhouse gas. This means warming increases atmospheric moisture, and that moisture can reinforce warming. It also changes precipitation. Storms in a warmer atmosphere often have more moisture available, which can increase the intensity of rainfall. At the same time, higher evaporation can dry soils more quickly between storms, especially in regions already vulnerable to drought. This helps explain why seasons can seem both wetter and drier. Depending on the timing, The problem is not contradiction. It is a more forceful water cycle operating in a warmer world. Feedback loops deepen the transformation. A feedback loop is a process in which an initial change triggers effects that either strengthen it or weaken it. One important positive feedback involves snow and ice. Snow and ice reflect a large share of sunlight. When warming reduces snow cover or melts ice earlier, darker land or water is exposed, darker surfaces absorb more solar energy, which produces more warming and leads to further snow and ice loss. Another feedback involves dry soil. When soil dries, less of the sun's energy goes into evaporation and more goes into heating the land surface. That extra heating can worsen heat waves and deepen drought. Vegetation, cloud cover, and fire can also participate in feedbacks that strengthen regional seasonal change. The oceans play a major role because they store most of the excess heat added to the climate system. This stored heat affects the atmosphere through sea surface temperatures, evaporation, and changing circulation. Warm ocean water can feed heavier rainfall, delay coastal cooling, and influence the large-scale patterns that steer storms. Yet the oceans do not warm uniformly, and their natural variations still matter. Cycles such as El Niño and La Niña continue to shape American weather from year to year. The difference now is that these natural variations operate on top of a warmer baseline. A familiar pattern may still recur, but the temperature, moisture, and impacts associated with it may no longer match historical experience. Aerosols add complexity to the picture. Aerosols are tiny particles suspended in the atmosphere. Some come from natural sources such as dust, sea spray, and volcanic activity. Others come from industry, transport, and biomass burning. Certain aerosols reflect sunlight and can produce temporary cooling, while others absorb heat or affect cloud formation. Because aerosols are short-lived compared with greenhouse gases, their influence varies more by location and time. They can modify regional climate and seasonal expression, but they do not cancel the long-term warming caused by greenhouse gases. Instead, they add texture and unevenness to the pattern. Land use change also matters. When forests are cleared, when cities expand, when wetlands are drained, and when irrigation changes the moisture of the land surface, local and regional climate can shift. Vegetation influences how much sunlight is absorbed, how much water is returned to the air, and how rough the land is to passing winds. Croplands behave differently from forests. Pavement behaves differently from grass. These differences can alter temperature and humidity locally, and in some places they modify the seasonal experience strongly. Yet these land changes usually act as amplifiers or regional modifiers within the larger warming system driven by greenhouse gases. The reason the effects appear uneven across America is that climate is not simply temperature added to a map. It is a moving interaction among air, water, land, and ice. Mountain regions respond sharply because small warming can raise the snowline. Coastal regions respond through ocean heat and moisture. The South responds through humidity and long warm seasons. The Southwest responds through evaporation and drought. The plains respond through changing contrasts among air masses. The Great Lakes respond through warming water and declining ice. Cities intensify heat because of their materials and structure. Each region translates the same planetary energy imbalance into its own seasonal language. Scientists understand these causes through many lines of evidence. Direct atmospheric measurements show rising greenhouse gas concentrations. Laboratory physics explains how these gases absorb infrared radiation. Surface thermometers, satellite records, ocean measurements, glacier loss, snow decline, and biological timing all show consistent patterns of warming and seasonal shift. climate models, built from physical laws and tested against observations, reproduce the broad changes only when human-caused greenhouse gas increases are included. Natural factors alone, such as solar variation or volcanic activity, cannot explain the full modern pattern of warming and altered seasons. Uncertainty remains in the exact pace and regional expression of future changes, especially regarding rainfall patterns, storm tracks, and the timing of particular extremes. But the central cause of the seasonal transformation is well established. This means the unsettling behavior of the seasons is not a collection of unrelated curiosities. Earlier blossoms, later frosts, heavier rain, shrinking snowpack, warmer nights, prolonged summer heat, weaker winter ice, and delayed autumn cooling all emerge from the same deep shift in the climate system's energy balance. The old seasonal forms remain visible because the Earth still tilts on its axis, still circles the sun, and still distributes sunlight through the year in the same astronomical pattern. But the atmosphere and oceans that receive and redistribute that sunlight are warmer than before, and so the meaning of the old pattern changes. At the deepest level, the seasons in America are no longer acting normal because the physical system that shapes them is carrying more heat, more moisture, and more imbalance than it did in the past. The calendar remains, the orbit remains, the angle of light remains. Yet within those constants, the moving parts of climate have shifted enough to redraw the year from the inside out. What people feel as strange springs, relentless summers, hesitant autumns, and unstable winters is the surface expression of that deeper change, a planetary energy problem translated into the intimate language of season. The year still turns with the same celestial order. The Earth leans on its axis. Light shifts north and south through the months. Days lengthen, then shorten. Winter light remains lower and weaker. Summer light remains higher and stronger. Nothing in that ancient motion appears disturbed. Yet on the ground, in the air, over the water, and through the bodies of living things, the familiar structure built around that motion no longer settles into place as it once does. Across America, the signs gather quietly. Snow arrives later and leaves earlier in many regions. Warmth enters spring ahead of its old schedule, but cold still returns often enough to unsettle the land. Summer expands beyond its former bounds and stays through the night, stored in water, stone, soil, and pavement. Autumn loses part of its steady cooling, and winter grows less continuous even where cold still holds power. Storms, rivers, forests, fields, cities, insects, birds, and people all begin to move under a calendar that still exists, yet no longer guides the same sequence. What changes is not the existence of seasons, but their character. Their edges blur, their timing slips, their inner order weakens. The country still passes through cycles of growth and rest, heat and cold, wetness and dryness. But the balance among these states grows harder to trust. Observations show that this is not illusion, and not a passing irregularity. It is the visible expression of a warming climate system carrying more energy and more moisture than before. In that altered system, the old seasonal memory remains like a faint map beneath a new one. The outlines are still there, but the roads no longer lead by the same turns. The land continues to receive spring, summer, autumn, and winter. It simply receives them in forms that feel less settled, less distinct, and less familiar than the generations before had known. And so the year goes on, calmer in the heavens than on the earth below, while the seasons continue their slow and measurable change,